Right, conservation of momentum. Part of the reason we love momentum so much is because, like energy, it's conserved. As I said, this is I personally think it's quite a it's a slightly profound realization to recognize that although we always talk about energy, we're always going on about energy, not only specifically in physics but also in politics and life in general. The only reason in physics we're actually interested in this artificial mathematical construct, half mv squared, mgh, and all these, we've got like so many different mathematical expressions of energy that don't really seem to have anything mathematically to do with each other. The only reason we're interested in all those specific odd-shaped blocks of maths is because it happens to be conserved. If it wasn't conserved, there would be nothing particularly special about those equations. And the same is true of momentum. Momentum's nicer. It just looks nice, doesn't it? Mass times velocity. That seems like it should work. Whereas energy is always a little, I don't know. This is a slight personal philosophical insight, but yeah, the world's a beautiful place. Right, momentum. As you've probably been staring at for a couple of minutes now, momentum is equal to mass times velocity. During collisions, you can transfer momentum, but the total momentum in the system is always conserved, regardless of whether you're losing energy or not. The momentum's always conserved. So long as no external force acts. So if you've got two balls colliding, and so long as I don't, rush in there and push one of the balls myself, the momentum will be conserved. Momentum is a vector quantity. It is a scalar, mass times a vector. So it is itself a vector. With direction, when considering a problem, we must select a direction to be positive. We've encountered this concept several times today. We need to establish a convention and stick with it. Right. For momentum questions, I know they seem simple. You're talking about two balls. How bad can it be? It's pure hubris, I assure you. Be neat, be careful with your accounting for these questions. I don't mind whether you want to use different symbols for velocity or momentum afterwards and before, whatever works for you, but just make sure you don't get confused, because these questions can and rapidly do become a sort of quagmire of indices, these little numbers. So beforehand, the total momentum, defining right as positive, P1 minus P2 equals P4 minus P3. Therefore, you have M1 V1 minus M2 V2 equals M2 V4 minus M1 V3. And then you can imagine once you start dividing those across, you can end up with all sorts of things, and they all look pretty similar, and horrible. Right, let's do an exam question, and then that should take us to the end of this session. We'll have I believe it's 15-minute break. Good, excellent. Okay, we're in the home stretch, don't worry. Consider the diagram below showing a rocket of mass. So as soon as you see rocket, it's something to do with conservation of momentum and Newton's third law, perhaps. Of mass, 7.5 tons, traveling through space at 60 meters per second. Fuel tank of mass. Oh, okay, so we've got two separate masses for the fuel tanker and the rocket itself. The rocket detaches the fuel tank, after which the fuel tank travels in the original direction of motion with velocity 45 meters per second. Determine the velocity of the rocket after the fuel tank detaches. Sweet, love it. Determine That's our command word. It's in the category of calculation. 3 marks should be 3 stages. Okay, so before they're together, they're traveling at 60 meters per second, and their combined total is 39,500. Okay. They then separate, and we are told only about the case beforehand. Right, we've got mass of rocket and mass of tank. And we are going to want to, well, we've got V tank already, but let's call this V rocket. Lovely. So the total momentum before is equal to the total momentum after. Total momentum before, simply multiply these two numbers together. Lovely. Big number, but not to be feared. Right, after detachment, you've got 2 contributions. You've got the tank, which is lovely because we know both of these. Hooray, hooray, hooray. Afterward, and we've also got the rocket. We know what this is, but we don't know what this is. That is what we want. Okay, so we've got an expression in terms of V rocket. Last thing to do is set these equal to each other because momentum is conserved. Fab. Yeah, sorry, that's just rearrange. That's sort of just neatening up this line, and then we're equating the two. Okie dokie, rearrange for V rocket. It's 124 meters per second. Does that make sense? Looking back at my question, yes, it makes sense that this is going faster, not only than this, but also it should be going faster than this. Otherwise, detaching was an exercise in futility. The point of detaching is that the rocket can go faster. So our answer is still on the same order of magnitude, but it's bigger than 60 meters per second. Right.